Gopika, are you there? Can you please unmute and start the proceedings?
Hello? Hello, sir?
Yes, yes, Gopika, you are audible. Please go
Yes,
ahead.
sir. Yes, sir. Good evening, everyone. Welcome to the first L4 series talk on energy efficient simultaneous wireless backscatter and power communications. This is Gopika, MTTS Chapter Chair of IAST Student Branch. It's indeed a great privilege to partake in this grand event, which is honored with the presence of the luminaries of the discipline. This L4 Talk series is organized by IEEE MTTS Kerala chapter in association with MTTS student branch chapters of GEC, Button Hill, and IAST. It's our pleasure and privilege that Dr. Nuno has accepted our request to deliver this talk. Welcome, sir, and thank you for joining us today. I welcome all the dignitaries and participants to the much awaited section of the evening. Before we get started, I'd like to draw your attention to a few things. The participants will have the opportunity to submit their queries into the chat box. You may send your questions at any time during the presentation. We'll collect these and address them during the Q&A session at the end of the talk. We also request you to turn off your audio and video and maintain the same throughout the session. As you all are aware, today's speaker is Dr. Nuno Borges Carvalho, University de Aveiro, Portugal. Hope I pronounced correctly. I know that I might have mispronounced. Please excuse me, sir. Now, for the detailed speaker introduction and moderation, I request Dr. Chinmay Saha, MTTS Kerala Section Chair, to take over the virtual podium. Over to you, sir.
Thank you. Very nice event till now, so I don't want to extend a talk. Rather, we will move to the technical part. Professor Nuno Borges Carvalho, he is a really leader and legends, which is the tagline of the event. He really doesn't know any introduction. He has contributed immensely in this particular field of wireless power transfer. I had the privilege to meet him quite a few times and had some discussions also during IMAT 2019. So it is my pleasant duty to introduce formally Professor Nuno, who is a fellow of IEEE in 2015, was born in Luanda, Angola in 1970. He received the diploma and doctoral degree in electronics and telecommunication engineering from the University Aveiro, Portugal in 1995 and 2000 respectively. He is currently a full professor and senior research scientist with the Institute of Telecommunication University of Aveiro and IEEE Fellow. He co-authored Intermodulation in Microwave and Wireless Circuits, Arctic House 2003, Microwave and Wireless Measurement Techniques, Cambridge University Press 2013, White Space Communications Technologies, Cambridge University Press 2014, and Wireless Power Transmission for Sustainable Electronics, Wiley 2020. He has been a reviewer and author of over 200 papers in magazines and conferences. He is the editor-in-chief in Cambridge Wireless Power Transfer Journal and associate editor of the IEEE Microwave magazine and former associate editor of IEEE Transactions on Microwave Theory and Techniques and IET Microwave Antennas and Propagation Journal. He is the co-inventor of 6 patents. His main research interest includes software-defined radio from end systems, wireless power transmission, nonlinear distortion analysis in microwave wireless circuits and systems, and measurement of nonlinear phenomena. He has recently been involved in the design of dedicated radios and systems for newly emerging wireless technologies. Dr. Borges Carvalho is a member of IEEE MTT at COM, the past chair of the IEEE Portuguese section, MTT 20 and MTT 11, and also belong to the technical committee MTT 24 and MTT 26. He is also the vice chair of the URS Commission A Meteorology Group. He was recipient of 1995 University of Aveiro and Portuguese Engineering Association Prize for the Best 1995 Student at the University of Aveiro, the 1998 Student Paper Competition of IEEE Microwave Theory and Techniques Society, IEEE MTTS, International Microwave Symposium IMS, and the 2000 IEEE Measurement Prize. He was a distinguished microwave lecturer for the IEEE Microwave Theory and Techniques Society So as I mentioned, he has contributed immensely technically in this vast area of megahertz to terahertz, gigahertz to terahertz technology, and he's also a true leader. I mean, always helpful, supportive. I get the reply to him very, as soon as I write, immediately I get a reply. Thank you very much again for accepting our invitation. So I now request you to kindly take over this virtual podium and start your talk. Thank you very much. Over to you, Professor Nuno.
Okay, thank you very much, Professor Saha, and thank you very much, Dr. Gopika, for the introduction. And I will share my screen now. So, bye. Hopefully, can you see my screen?
Yes, sir.
Yes, sir. Okay, good. So, first of all, as I said, thank you very much for the invitation today. It's really a pleasure to be in this inaugural talk and be sharing my experience and what we have been doing in my research group over the years. So, let's see. Okay. So, first of all, let me say from where I'm seated actually in a room in my hometown. The COVID-19 created this situation where we have to be inside houses without any chance to actually meet our friends and meet our colleagues and travel around the world to discuss interesting things. But hopefully the WebEx and Zoom tools allow us to actually be all over the world to give these talks to everybody. So I'm based in Portugal, as Professor Saha said, and in Portugal I'm also based in Aveiro. So I would like to have a pen here so you can see images for a moment. So okay, so I'm actually based in this very small town in Portugal. I have a very nice group of students. Actually, most of the work that I'm going to show today and I'm going to discuss today are mainly due to students. Students are a big, or let me put it this way, are the main part of our activities. So this is a very interesting area, and all students that can get to us, that can work with us, are very, very welcome. So let me also say that in my group, we are a group, despite we are a group from university, we have been working with a lot of companies. So here you can see some of the companies we have worked over the years, and these actually show you that our work and what we do in our lab is as a significant collaboration and a significant number of companies that are actually teaming up with us in this respect. So in order for you to understand a little bit from where we came from, so we work mainly on several applications, from nonlinear distortion to microwave and measurement schemes to actually wireless power transmission, and this is our more recently work. So wireless power transmission is something that we have been working for several years up to now, and we have been actually doing some interesting works combining wireless power transmission and communications. So here, this slide shows you a little bit of my group. So my group is working on mainly UAV and satellite communications. It's very good that today here we are in a space-based agency related chapter. So I will try to push a little bit of my talk to that area, but we have been working with UAV communication systems. We have been working with MMIC design, as you can see in the middle of the screen. And in the bottom of the screen, you can see actually commercial products that were actually proposed by us to some of the companies we engage with. And these are mobile and wireless communication products for several applications. And I was also the chair of a big group in Europe devoted to wireless power transmission, or wireless information and power transmission. And this was a group of universities from 20 different countries in Europe that actually worked towards this goal. So I would like to start today, and the first part of my talk today is really on how much energy I really need to do a wireless communication. So how much energy I need to produce to actually communicate with the world. And if you go back in time, if we go back into the beginnings of time, when we start to do communication, what we see is that our first communication scenarios were done using fire. So actually you burn fire, you create smoke signs, and you actually, when you do this, you do transmission by smoke and transmission by signals. Well, then you move to actually pigeon-based communications, and this was done several times. Even in the First World War, we used pigeons to actually transmit information from one side to the other. And by saying this, what I want to share with this slide is that despite we start with fire and then we have the pigeon for doing communications, you can see that the amount of energy we need to expend to do bit per second communication was very, very low. So the efficiency at that time was extremely low in this scenario. So you can say, and I'm joking here, of course, but you can say that we spend a lot of kilograms of wood to bit per second, and we create a lot of CO2 emissions, and a lot of corn also, if you want to do it like that. But if you look to the time frame of what we do, so we start with smoke signs, we move to pigeon-based communication, then we have a computer. And when we start to have a computer, we were connected to the wall. So when you send a message, when you send an email, you are connected to the wall and you send that to the internet. So you extract all the energy from the power outlet. Then we move to a laptop. And what is the difference between the computer and the laptop is that when we start to have a laptop, you start to have wireless communication. So this laptop, the difference between these two is that in this case, the connection to the internet is no longer available. We are using wireless, but if you think about the energy, here you can take the energy out of the wall, here the energy is out of the battery. So you need the battery for this laptop to work, so you need the energy for that. And what we are seeing now is that this is going to explode. So we are going to start to have not only a laptop or a computer, we are going to have a mobile phone, a laptop, we are going to have a tablet, we are going to have a smartwatch. So the number of elements that we are going to need and the number of elements with the batteries that we need is really huge. It's significantly larger than in the past. And if you look to the evolution of mobile communications, you see that from 1G, 2G, 3G, 4G, if you look here, what you see that 1G, 2G, 3G, 4G, you see a person. And you see more or less one object, which was a mobile phone. In 4G, you start to include the tablets in the look. But when you go to 5G, you see that most of the time you don't see a person. A person here is almost irrelevant, because what we want is to connect everything to the internet. So we want to go to what is called the Internet of Things, the Internet of Everything. So everything is connected, everything is producing a lot of information, and we need to send that information wirelessly. And this is really where I have my problem. That is, when you go for these, I call it the bright smart future, when you go for this new road where everything is connected, we are going to start to have smart cities, we are going to start to have smart cars, we are going to start to have smart health, and we normally forget that in order that we have all these, the battery that we need is huge. And on top of that, there will be a lot of waste of energy. And we actually need to start looking here to this approach slowly. So let me share with you some of the reports that are out there about energy consumption of the wireless and the microwave, if you want, communication scenario. And what I show you here is, it comes from GSMA, which is a big consortia for mobile communications. And this was extracted for 4G communications. So what we see for 4G, and these are very interesting results, you see that we produce, and these are numbers that come from Nokia. So they actually pick up one country, a mobile operator in one country, and they start to look to how much energy that country needs to power up their mobile communication scenario. And what they found is that for a specific operator, they need 140 terawatt hour. That is the energy that the power plant has to create only to power up a mobile operator. And what you see is that 10% of the energy is lost in energy transmission. That is to bring the energy from the power plant to each of the base stations all over the country. So 10% of energy is lost there. Then you see that 30% of energy is lost in cooling, heating, lighting, UPS, storage loss. So this has nothing to do with the wireless communication. It's mainly to make the temperature in a several level, but nothing more than that. You don't really need it for the wireless if you don't heat the devices. Then what you see here is that a very strange thing, power supply fans. So the fans that you have in the power supply of the base stations, you lost 20% extra. And then what do we see? We see that most of the base stations are there day and night, but probably during the night you are not using them, but they are there, they are consuming power. So 70% goes to what is called redundancy. So I like very much this graph because it shows you that from the 140 terawatts hour that we actually create in the power plant, we only use 20 terawatt hour to transmit the bits. So this graph shows you a very interesting thing. Not only the microwave engineers are important to increase this efficiency of the transmitting of the bits, but more important than that, all the electrical engineers are important to optimize all the chain from the power plant to the base station. And if you go inside the base station, which is here, if you go inside the base station, what you see? You see that 40% of the energy of the base station is for the power amplifier. And 37% of the energy goes to air conditioning. So what that means? It means that since the power amplifier does not convert all DC power in RF power, a significant part is converted in heat. So if it is converted in heat, you need an air conditioning to reduce the temperature down. And when you need that, you increase the air conditioning spenders. So what that means, it means that if I optimize the power amplifier, if I optimize the RF part of my circuit, I can optimize the overall picture of this. And I would like to, when I click on the button, you'll see an even worse thing, which is from a Huawei white paper. This white paper is from last year. You see that Huawei predicts that 5G communications will have a demand of extra 300% energy compared with 4G. So what I'm saying here is that all these 3G, 4G, 5G are a great topic, but we have to be careful because we are expending a significant number of energy to actually do the communication. And you can say, okay, but it's for profit of humanity. Yes, it is, but most of this energy is not devoted to wireless communications, as you can see here. Most of this energy is spent because we are not high efficient in these devices and in these solutions. So let me show you another example from another point of view, which is the Internet of Things. And what you see here, this comes also from a report, and you see that the number of IoT devices are going high very fast. And it's very interesting to see the standby energy for most of these solutions. So the standby energy for most of these solutions actually is increasing, and as you can see, the standby energy is also on the order of terawatt-hour. And so how do you have this standby energy? Well, because these are IoT devices, they are based on batteries. So what you see in this graph is not only that we need a lot of batteries, but what you see in this graph is what is called battery manufacturing. What that means? Well, if you need a battery, you need power to actually create the battery also. And it's interesting to see that the amount of power you need to create a battery is 3 to 4 times the amount of energy the battery contains. So if I need 1 million, 1 trillion values of batteries, then I need a lot of power to actually create that batteries. And on top of that, at the end, what is going to happen? Well, at the end, you're going to throw away your battery. Most of the people do not recycle. So the battery will create waste, will create pollution. So this is a big problem. And one of the things that we have to try to start thinking is, can we remove the batteries out of all these gadgets and out of these IoT devices? So only for you to have a very simple example, we did in Portugal. So again, Portugal is this very tiny country that you see here. This is Europe. And what we saw is that in Portugal, we have around 23 millions of batteries wasted every year only to change the channel on your TV, only to have to do TV zapping. So one of the things I will not show today, but one of the things we did was actually to create a remote control without batteries. Because if you need to change the batteries of your remote control, only this tiny country, which is Portugal, and we have, as you can see here, 4 million residences, so it's not a big country, we spend 23 millions of battery that go to garbage, and this is really a problem. So what I would like to show you and what I would like to discuss with you today is how can I minimize this energy footprint? How can I overcome this energy footprint, and how can I optimize the energy consumption of our RF and wireless systems? So let's look, and the first part of my talk will be devoted to mainly to IoT in the household. Then the last part of my talk will be devoted to IoT for space applications. But let's look at the IoT for household applications. Ideally, in the future, you'd love that your house will have IoT connection all over the place. You want to know how much water you are consuming. You want to know how much the alarm that you have there. You want to know how much light you have in the house. You want to know the temperature. You want to know a lot of things about your house. So these IoT devices should be very low cost. They should be deployed massively. You need trillions of these devices, and they should be low power sensors. So this is really my problem. How much power is low power? If I ask each one of you how much power is low power, you'll probably say 1 microwatt is low power, but someone says no, 1 microwatt is high power. So 1 nanowatt is low power, 1 picowatt, 1 femtowatt. So the problem is how much power is low power. So we decided to do a very simple test. So we gone to the market and we pick up 2 ships. 2 available commercial ships. One is what they said is a ship for the RF part of IoT sensors. So this is a very well-known company, I will not say which one, is a sub-1 gigahertz chip. And if you see here, it says that the supply current in power down mode is 2.5 microamps. Now, that's good, that's not very high power, but it also says that the supply current in receive mode or supply current in transmit mode is around dozens of milliamps. So if you multiply this by the minimum supply voltage you have, you need around 70 milliwatts to transmit and 24 milliwatts to receive. I know it's a short time, you send a message and you go to sleep, but you need that power to transmit and receive. Well, on this side, what I have is a similar thing for ultra low power Bluetooth chip. And again, you see that the burst when you need to transmit or receive, it's around 9 milliwatts. So the question here is, okay, is this low power or is this a lot of power? And so let's see, and what we did, we pick up traditional batteries that you can find on the market. And each one of these batteries have a capacity. So it allows you to power up these devices for a certain amount of time. So we pick up one of these chips and we plot, as you can see here on the top, we plot actually how much years your sensor can live based on the transactions per day you will use. And you see that if you pick up the best battery, which is this one, you get, imagine that you have 10 transactions per day. Well, this device will live forever. But imagine that I want to locate or I want to see how much time my class door was open and closed. So each time a person enters a class, it opens and closes the door, and it opens and closes the door. If you assume that you have 50 students and several classes per day, probably that in order to understand how much time the door open and close, you spend more than 1,000 transactions per day. So what you see is this graph is exponentially. It comes down very fast. So this IoT sensor connected with the door, it's not viable if it has to use a battery. Why? Because you need to change the battery probably each year. And I don't want to change the battery each year for all the doors of my university. So this is not a solution to have IoT sensors with actually to have it with a battery. So how can I remove these batteries? So there are two things that I have to look. Can we eliminate batteries? This is a very important question. The other is, can we remove the need to power for transmit and receive? And we have started to look to the market. And what do we see? You see that you can have energy harvesting. So actually you can harvest energy all around to power up your sensors. We can have backscatter communications. This is a different paradigm of a traditional super-heterodyne communication. I will tell you what it is in a moment. And we can have wireless power transmission. What is this? I will transmit power wirelessly to my sensor. So the sensor does not need a local battery because you will receive power from the RF stage. So looking to what is on the market, what is energy harvesting? You can harvest energy from noise, from temperature, from ambient light, from movement. So you can harvest energy from all over the place. Well, the best ones are solar power, of course, but I need to be outside. If you are inside the building, it's more difficult. Well, you can have mechanical power, but in order to have mechanical power, you need the mechanical kinetics to actually convert energy. Or you can have ambient RF. What is this? I collect all the energy that is electromagnetic waves in the air, where this electromagnetic comes from Wi-Fi, it comes from GSM, it comes from radio and TV broadcast. You collect all this energy and you power up your device. Well, what is the problem with that? Well, the problem is that the ambient energy is around 1 microwatt per square centimeter, so it's very, very low. And hopefully it's low because you don't want to be in an environment where you have electromagnetic power higher than milliwatts per square centimeter. If not, it's going to be a problem for humans. So energy, or what they call electromagnetic energy harvesting, is interesting and it's very important if you want to create a sensor, for instance, that only communicates with the base station once per day. But if you want to have a sensor that is communicating all the time, this is not a solution. Unless I create a beam of energy, unless I create a beam of RF energy that is beamed to a device that will convert this energy back to DC. And this is what is called wireless power transmission. That is, I create energy, I beam this energy to a diode, sorry, and in the diode I convert that RF energy back to DC, and I can power up my device or I can actually charge a battery. Of course, the problem, as I will show, is that the efficiency of these systems for long-range communications is low. And this is where we are actually putting a lot of effort to work on this moment. And let me show you some of the things we have done in this respect. So one of the main circuits here is, of course, the transmitter. So you have to generate the energy, you amplify the energy, you send this energy using an antenna, normally antenna array, and on the other side you have an antenna array, and then you have an RF to DC converter, which I said is normally a diode, and then you collect this energy in a certain approach for or a battery or a sensor. Well, the RF to DC converter, as I said, is normally a diode. And what is the problem? The problem is that if you have a diode, a single diode, you have a sine wave. This sine wave goes through your diode and it gets rectified. So at the end, you see that you have a constant DC here, but you lose a lot of efficiency. Why? Because you need a certain amount of power to get to the knee of your diode, to get to the rectifier of your diode. If you don't have this voltage swing, you don't get to this knee, and then you don't have enough DC voltage to create this. So when you are far away from your transmitter, the amount or the amplitude of your sine wave is low, and if the amplitude of your sine wave is low, you don't get a lot of energy, and so the RF to DC efficiency is very low, in the order of, let me put 10% or even lower. So in a way we play a little bit with that. So we start to use, instead of using a sine wave, we create what is called a multi-sine. And so we send to our diode rectifier, not the sine wave itself, but the summations of sines, so that you have peaks of this sine. Why are these peaks important? Because they go harder into the nonlinearity. So they go harder into the rectification, and so your DC voltage will go high. And this can actually improve your overall RF to DC efficiency. But I want to show, I don't want to spend a lot of time here, I want to show that actually wireless power transmission is a viable tool, but all these equipments, all these circuits were normally not optimized for the energy efficiency of these devices. So this is something that we have to take care, and this is an example of what we do in the RF to DC converter, but there are many other things to do. Well, the other scenario is that, okay, this allows you to send power to the receiver, but the receiver, as we saw before, let me go back a little bit. As we saw before, the receiver and the transmitter needs around 20 milliwatts to transmit and receive. So even if I send power to my IoT sensor, I need around 20 milliwatts to transmit and receive. And why? Because most of these devices are based on super-heterodyne receivers and super-heterodyne transmitters. So you have an oscillator, you have a mixer, you have a power amplifier, normally you have a low noise amplifier. So the complexity is high. The question is, can we remove the need of power to transmit and receive? So not only we don't need the battery, but can we remove that need for transmit and receive? And the solution actually goes back to 1946 and goes back to what it's called the backscatter radio. What is a backscatter radio? Well, a backscatter radio started with this example here. This is a seal of the American Eagle, and this was an offer from the Russians to the US Embassy in Moscow. And this was made of wood. Purely wood. So when the Americans received this, they managed, they saw, they searched everything, and they said, well, this is a wood plate, so let me put it in the wall. So after, from 46, as you can see here, to 52, so only after 6 years, they start to understand that the Russians know too much of what they were doing inside the embassy. So they start to think, what can be, how they know this information? So they open this seal, and inside this seal, you can see this hole in the seal. This is made of wood, okay? And inside this hole, they saw a very tiny metal. This is an antenna. And on this tiny metal, they have this piece of metal there, which is a resonant cavity, a very small resonant cavity. And resonant to what? To my voice. So each time I talk, there is a tiny piece of metal here that vibrates. And if this tiny piece of metal vibrates, it will change the impedance of this antenna. So what is backscattering doing is, if I send a signal to my antenna, if I short circuit this antenna, what is going to happen? Part of the signal is going to be reflected. If I match the antenna, this signal is going to be absorbed by this load. So imagine that I can change the impedance of my antenna with a switch. Short, match, short, match. If I can do that, I immediately have a system that is able to is able to backscatter my information by on, off, on, off, on, off. So what I'm doing an amplitude shift key passive device. And how we can do that? Well, a backscatter is nothing more than a transistor. So a very simple transistor can do a backscatter solution. And actually a device like this, how it works, you have an antenna, you have your RF to DC converter, it creates a DC power that will power up your microcontroller, and this microcontroller is connected with your transistor so that you can switch on and off. That is, you short circuit an antenna, match antenna, short circuit antenna, match antenna. This is the basic principle of what is called RFID. So if you have this RFID, this actually what I'm showing you here is an RFID tag. Without the sensors is an RFID tag. The question is, if I want to create an IoT sensor and if I want to create or include these sensors, then I need to create energy to power up these sensors. And this is really the problem I have, because when I short circuit this antenna, I'm not receiving power at all. So we come up with an idea some years ago where we combine one frequency where we send energy to my sensor. So I have one frequency that actually goes through this matching network and goes to my rectifier, and I use another frequency to actually change the impedance of my antenna. This work that we did some years ago was done with Professor Shigeo Kawasaki from the Japanese Aerospace Corporation in order to use these sensors inside space probes. And I will show you in a moment, because if you have a sensor like this inside a space probe, it means that the sensor that you have there don't need cables for powering it up. So you can load a lot of cables from space probe, and the space probe will become light in this scenario. So let me show you how this works. This is actually a simple prototype. You have your antenna. Your antenna is a matching network that goes to a RF to DC converter, which is a rectifier. It goes to energy storage and controls a microcontroller. And then I have my backscatter, which is a transistor. So what I'm going to do here, this is the Smith chart. You see, I will use 1.8 gigahertz for wireless power transmission. That is only for receiving power. And I will use 2.45 gigahertz to actually send information back. That's why I call it simultaneously information and wireless power transmission. So what you see is that when this transistor is open, I have 0 volts here, both frequencies are matched. When I change this transistor to 0.6 volts, that is, I short circuit this transistor, the 2.45 gigahertz goes to almost short, so it goes to the top, to the exterior of the Smith chart, and the 1 gigahertz maintains in the center. So this circuit will continue to have wireless power transmission here, but we'll have a short circuit on the other side. So if I do this, you see the impedance at 2.45 gigahertz is on off, so it's amplitude shift key, but at 1 gigahertz the frequency shifts. So I have a continuous flow of wireless energy inside my chip. So in NAVAL, we pick up this idea and we say, okay, if I can do 2 impedances, why not create more impedances? So we create a group of transistors. Instead of using a single switch, we use several switches, and we over the top on this Smith chart a quadrature phase shift key. So actually we have 4 points, and we can increase the number of bits that we send. Well, and then we thought, well, why not create the IQ backscatter modulator, which is nothing more than, as you can see here, we have a power divider, we have 2 switches, and each one of these switches are delayed 90 degrees, so they have 90 degrees apart, so that you can create actually an IQ modulator. So what you see here is a 16 QAM overimposed in the Smith chart, so that we can actually send a lot of information on the same backscatter almost without using energy. Actually, the best results we have is something like this. So this is our prototype. You have the IQ backscatter modulator. You have the RF to DC converter here. And what you can see here, we have a 16 QAM, and the maximum we achieved was around 960 megabit per second, using for the transmitter, only for the transmitter, 61 femtojoule per bit. So this is extremely low. As you can see here, we are actually in this lower part of the graph. We don't need almost no power, but we achieve a lot of energy being transmitted back. So this was published in the transactions and on the components letter also, to show that this is viable for actually create an IoT sensor. And the idea is that you can have a base station, which is something like this. It can be a software-defined rate if you want, but we send energy to my sensors. The sensors do not use a battery, and they communicate back with the base station using backscatter communication. But in order to power up the sensors, we create at another frequency, we create a mesh of wireless transmitters, so that we can have one frequency powering up the sensors around the place, and we can have a single backscatter reader somewhere in the environment to receive this signal. So actually, this is what we have done for, let me put it this way, terrestrial implementation. The thing is, can we bring this for space exploration? So I decide today, also I have 10 more slides, so I can show you how can we move this for space. And why? Because I know that you have a lot of colleagues that work on space at this time. So if you go to a space power and energy storage roadmap, you see that there are a lot of energy needs in a space probe. This is very, very important again. So this is not only a problem of I'm creating pollution. No, it's a problem of if I reduce the power the space probe is using, I can improve a lot of other activities in the space. So how wireless power transmission is being looked for space? Well, there are a lot of approaches for wireless power transmission using space environment. The first and the most interesting one is this space solar power, where the objective is that you create huge solar conversion, so solar panels in space. You collect the solar energy there, and why there? Well, because you have 24 hours of solar. It's more, you don't have clouds, so you are receiving solar all the time, so the efficiency of the solar panels is much higher. Then, what is the idea? Well, the idea is that these solar panels will create an electromagnetic beam in space, and it will bring it to Earth. So what you see in this slide here is actually the antennas on the Earth that will convert RF signal back to DC and will power up the device. So this is an idea that is there since the 60s. So this was mainly a proposal, but there are people actually following these ideas. These are some of the most recent results from Japan. So this is a Japanese wireless power demo in 2015. You can see here the transmitter and the receiver. This was done in the Earth. to show up how it works. As you can see here, this worked at 5.8 gigahertz with 1.8 kilowatts. Well, this is actually very recent. Actually, this was a wireless power demonstration from the NAVAL research lab in the US for the same approach. You see the solar panels there, the antenna there, and this is one cell of this approach. So this is very active at this moment, and there are also some, and I took this from the web, so the China is also looking to how can we achieve this power in space and bring it to Earth. Well, I'm showing you this here because this is not the IoT concept I was telling you, but just to show you that wireless power is something that in space is becoming very important and is becoming very interesting to see. These are, of course, the craziest ideas that I have heard, but this is something that we have to look to be able to actually follow this approach. But there are other applications. So it would be nice if instead of having this wireless power from Earth to ground to power up power plants in Earth, we can do other things with wireless power in space. We can power up space probes. I will show you that in a moment. We can power up planet explorers. We can remove the cables from sensor probes inside the satellite. And we can use these passive sensors around the satellite or the space probes for health monitoring of space probes itself. And there are some examples. I will show you one example here. So this is a very simple example of that happened last year in ISS. This is also an experiment for National Research Laboratory, Naval Research Laboratory, sorry, in the US, where this astronaut was showing that she can collect wireless power for a small device using the Wi-Fi connection on board. So what that means, it means probably that some of these sensors probably do not need the battery and do not need cables. So they can reduce the amount of cables, they can reduce the amount of batteries they will need there. Well, this is another example from NASA. These are called the rings. What is this? These are inductive coupling rings that goes around the space ISS, and this is the wireless power receiver. So why do you want to have this? Well, because sometimes they need to have a camera outside the ISS to see damages on the structure. And this camera has a cable for powering, or it has a battery and someone has to go there. So with these rings, they can actually have these rings floating around and having energy extracted from the ISS by inductive coupling. So this is a nice project that they did some years ago. But what we, 3 years ago in my university, we start to look was, can we create an IoT group of cells for space exploration so that we can have a very low orbit satellite that should be close by my space area, and can I send these probes, and these probes can be powered by this low orbit satellite? So what we start to look was to the Rosetta mission. I don't know if you are aware of this. This was a mission sent by the European Space Agency to monitor a comet. So they sent the Rosetta mission. Actually, it was an orbiter, like a satellite if you want, and then you have a lander. And this lander actually get out of the orbiter, and the lander was called Philae, and it landed on the comet. So the idea was what is you get the orbiter, you send the probe to the comet, and then you monitor a lot of information about the comet. You will receive the signal back to the orbiter, and this orbiter sends the information back to Earth. What happened? Well, what happened is that this lander, the Philae probe, when it landed on the comet, it got to a shadow of some kind of rock or something like that in the comet. So what happened is that the Philae probe was prepared, it has a battery, and was prepared to receive solar light to power up the battery. But since she got in a shadow zone, after some hours of operation, it disconnected, no more power. So what that means, it means that we spend a lot of millions, trillions of dollars to get there. A very, very nice project. But when the Philae gets to the comet, she was lost due to the power restraint. This is really a problem. And what do you see? You see some interesting things. Look to this image. In certain days, the orbiter was close to the probe 6 kilometers away. It's not 100 kilometers away. It's not 1,000 kilometers away. It's 6 kilometers away. So what that means, it means that if I have an opportunity to create a wireless power transmission link, if I have the opportunity to create an information and wireless power, I don't need a battery to actually extract the information out of my probe in the comet. So I will not need that battery dependence at this point. So what we did, and very fast because I think I'm spending a lot of time. So what we did, we go and we see, can we actually build something like this? So we pick up our traditional wireless power system. You have a generator. What is a DC to RF? You have an amplifier, you use an antenna, you beam an antenna for the other side, the receiver, RF to DC converter, and look to that. Well, the problem is that if you start to multiply the efficiencies of the generator, the efficiency of the power amplifier, the efficiency of the antenna, and so on, you put all these in an Excel file and you see the DC to DC efficiency is very low. Around 2% if you use state-of-the-art equipment, and I'm assuming in this situation that I was at a 6 kilometer distance from the transmitter to the receiver. So this actually was the start of a lot of works that I've been working with my PhD students, that is, how can I improve DC to DC efficiency for wireless and information transmission. And you have to improve the DC to RF efficiency. Mainly, you have to improve the efficiency of the power amplifiers. You have to improve the RF to RF efficiency. That is, when you create two antennas, a transmitting and receiving antenna, I cannot use the traditional beam that we normally use for telecommunications. I need to create focus of energy. So I need to focus my electromagnetic beam rather than beaming the efficiency. And we need, as I showed you in the first slide, we need to improve the efficiency from the RF to the DC conversion. Well, for the transmitter part, I cannot, and I don't want to use these traveling wave tube amplifiers because they are very large. So we start to use gallium nitride power amplifiers. And some of the things that we have been working on is on MMICs that can actually be connected directly to the antennas, so that actually each element of my antenna has an amplifier embedded, so that you can optimize this relationship between your amplifier and your antenna. And we create actually an active antenna array that creates a focus of energy in one sensor, and these sensors have a signal, actually is a backscatter signal that goes back with information of how much power they are receiving. So with that information, you can optimize your antenna to focus the energy here, to focus the energy there, and to focus the energy there, and so on and so on. So actually, if you know where the sensors are, you can go and focus and going around and focus energy in each one of the sensors. So these are some of the examples of the transmitter we have. This is the power amplifier MMIC that we designed using gallium nitride technology. This is actually how our antenna is working when you have your feedback channel, so it's focusing more in one direction or the other depending on the power. So we call this power on demand. So it's the receiver that is requesting for power. And this is actually the prototype that we had in our lab. So this is the transmitting antenna. These two antennas are the beacon. So this is the feedback antenna they receive to understand where they have to point their beam. And this is the receiver antenna. So actually, since when we send this antenna to a probe. We don't know from where the power comes from. We developed this structure that has antennas all over the place, and we have a solution actually based again on backscatter that can select the best antenna to maximize the efficiency from transmitter to receiver. Well, I saw one of the questions that was moving around. So for the RF to DC converter, we use two approaches, a Schottky silicon-based diode, and more recently we are using gallium arsenide for the receiving diodes at this point. So this is actually our receiver. You can see that the antenna is around. We have here, this is the receiver from the beacon that comes from our sensor, and this is actually a characterization structure that we use to show that we can create the focus of energy. So I think this was a long talk, sorry about that. I just want, before I finish my talk, to tell you that we are building a community which is called the wireless power transfer.ieee.org. So this is a community that is being sponsored by MTT, and the idea is to bring everybody in the world that actually works on wireless power transmission in this area. So this website is being updated. I believe until the end of the month we are going to have a very interesting website to have a lot of information, free short courses about wireless power transmission. So thank you very much for the invitation again, and this concludes my talk. I'm open for questions.
Gopika, you are there to moderate the question and answer part?
Sir.
Okay.
Sir, am I audible?
Yes. You have a question? Please go ahead.
Okay, sir. I had a note from our principal which I had to show here. So our branch counselor is also available. So if it is possible.
Yeah, definitely. Yeah, we can do it after the interaction part.
Ranjit sir, is it
okay,
fine?
Please go ahead. Yeah.
Can we, sir?
Yes.
No, we can do that after the interaction.
Okay, sir.
Yeah.
Thank you, sir.
Yes. So, Professor, thank you very much for the excellent talk. And in fact, we are following some of your works, and some of my students are reading your articles. Very good and very informative, broad spectrum of wireless power transfer you have covered. So there are few interesting questions, few are interrelated. So I'll take few from the chat box, and then I have also few queries from my own side. So one interesting question I see here is the medical applications for implanted devices for wireless power transfer. So it's a generic, and there are a couple of similar questions. So if you can cover that in a generic manner.
Yes. So for the implantable medical devices, it depends a lot on what you are discussing. So this is not my main field. So we have not been working on implantable devices. Most of the things that I've seen are low frequency. So we are talking about mainly inductive coupling solutions for that. I know there is a colleague in Washington University working on around 400 megahertz far field wireless power transmission for medical implants. the question I'm seeing here is how much efficient it is. Well, if you increase the frequency, the efficiency comes down, mainly to the way you actually interact between your transmitter and receiving antenna, and mainly of what is being used at most in recent times. But I can tell you one thing, that I have not seen, and this is something where we are actually trying to work a little bit now. I've not seen backscatter for medical implants very significantly being used. So what we are trying to do now for some medical related stuff is to actually create RFID type sensors for medical implants. And in that situation, even if the efficiency is not high, you can include these medical implants inside the body, and you can actually communicate with that medical implant without use of a battery. What that means, it means that you don't have to change the battery from time to time. So this combination of backscatter in some of these implants can somehow improve significantly the way we are doing this. The most recent example we have explored is a thermometer. So we want to measure the temperature of a person, but without touching the person and without using these infrared solutions that you see around. So what we have been trying to explore, and actually we submit a paper now for the IEEE Radio Wireless Week, is to design an RFID where your antenna impedance changes with the temperature of your body. And we show that it's possible to monitor variations of your antenna impedance by changing the temperature of the body, so you can actually mimic a temperature sensor in your device by using an RFID tattoo or something like that. So there are some applications that I think should be nice to look and explore, but as I said, I'm not working on that field very often.
Thank you very much. Of course, this wireless power transfer for biomedical applications, especially for implanted devices, is quite challenging. And probably, as you mentioned, it is in nascent stage, and few groups are trying to do something. I remember I was in wireless power transfer conference in 2018 at Montreal. So there was a few groups who are trying to propose certain interesting result at that time, but it is at the very early stage, we can say. So, sorry, there is one query regarding type of rectifiers. Which variant of Schottky diodes are used for space-based WPT rectifiers? I guess he's talking about the intermediate circuit, the matching circuit kind of thing.
Yes, so for space applications, there are two approaches. So we have been using gallium arsenide diodes for very low power rectifiers, and we have been using gallium arsenide transistors working as rectifying structures. And this is mainly for the Rosetta mission approach that I show you. The amount of power that we need to extract from the RF to DC converter was around 10 watts. And in that moment, we don't use diodes for the RF to DC converter. So we use transistors operating as rectifying structures. And they are based on gallium arsenide. This is what we have been exploring recently.
One of the related query from my side, as we all know, that one of the challenges for wireless power transfer and also in the energy harvesting is kind of having a broad matching bandwidth. So antenna wise or some other circuit wise, it is fine. So what is your comment? Of course, it is theoretically limited by that Borges criteria regarding the matching bandwidth. So, I mean, how much of effort is being devoted by your group in that particular area, and how we can mitigate those inherent challenges to achieve a wider matching bandwidth? Can you kindly comment on that side?
Yes, no, there are, for the matching approach, there are two two axes. One is the frequency of operation, and it depends a lot if you really need to do wireless power transmission in different frequencies or if your frequency is fixed. This is one element of the bandwidth issue. The other is on the power. So since these are based on diodes or rectifying structures, if you increase or reduce the power, the matching network will be no matched because your diode will operate in a different power zone. So what we are doing recently is to create adaptable matching networks by using other type of materials as resonance structures. So instead of using traditional traditional capacitors and inductors, we are actually exploring ferroelectric materials recently to try to cope with wide band, but as I said, it's not necessarily the frequency that we are worried about, is mainly the variation of our power, because we want to guarantee maximum energy efficiency when we change the input power. So we are trying to use other materials for the matching network development. And I think is the only way you can actually cope with this amplitude variation. So they are like non-linear filter structures, if you want.
Yes, yes. Thank you very much. One more question from one of the participants is, should we really be concerned about increasing the peak to average power ratio for the transmitting signal? So I know this is from someone who is doing work in this area. Should I repeat it?
Yes, so the peak to average power ratio in the transmitting, you have two problems. If you use the traditional approach where you have your signal and create a peak to average power, high peak to average power ratio, it goes through a power amplifier and then you degrade the power amplifier. Or the power amplifier starts to saturate the peak and then you lose the peak approach to the RF to DC converter, which is what I want. Or you have to do input power back off and you reduce the efficiency of the transmitter. So we did a different approach. Since you have an antenna array, and we are using multi-signs for creating this high peak to average power ratio, why not use each element of the antenna sends a different frequency of the multi-sign? So at the air interface, you'll see a huge peak to average power ratio, but each element, each cell of your antenna array will only operate one frequency. So you can bring it to class F, to class C power amplifier, so you can bring it to the high efficiency as you want, but it's really on the space that is on the air interface that they combine together to create high peak to average power ratio. I hope I answered the question. We have a paper on that on the transactions.
Right, right. Yeah, so you have addressed it very nicely. A couple of more we'll take because there are a lot of queries, but I know the candidates or the participants can interact with you later on. You have always been very generous. Yeah. So there is the question is not pretty clear, but how good is the this technique compared to the solar panels placed directly on the Earth? So the solar panel that NASA was also had some kind of initiative that Ali had with his group. Yeah.
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 Well, the difference is that you don't have clouds in space, so the solar panels will see the sun much more time than in Earth, and you can have large areas, very long, big areas in space. So, moreover, the efficiency, you don't go through the atmosphere. So you put the solar panel outside the atmosphere, so the efficiency will go higher very fast. The problem, of course, is then you have to convert that to RF signal and beam it to ground. And this is where the problem starts, because you have the far field interaction here. So one thing that I've seen, and I think the Chinese group is doing, which I think is a very good option, is to convert solar to DC to create a laser beam to an intermediate stage. So you have a laser beam up to a certain stage, then you have a high altitude platform, and the RF energy only comes from the high altitude platform to the ground. So you have three stages. So you collect the solar, you do laser beam transmission, power transmission, and then you use RF power transmission. I think this is a very interesting idea because the laser power beam is much higher efficiency than if you use the RF at this point.
Yes, yes. Thank you very much again. Now we can take one or two open questions, not from the chat box. If anyone wants to unmute and ask a question to Professor Carvalho, you may please do that. Okay. So if not, see Professor Gupta and Professor Poddar also still present. So if you can offer some comments regarding the talk and the future and any other thing in general.
Yeah, this was very exciting talk Nuno has given, and the program was arranged very efficiently, effectively on time, everything. I'm very pleased. It was a very wonderful talk.
Thank you very much.
Yeah, also had very impressed, with the presentation. I think this was the angle, at least I have not thought about. So, it really challenged our thinking. But, I think, overall, I just want to congratulate the team in Kerala, the student branch chapter and the leadership. I know these are not very easy to put together, particularly in the present times when we are depending on virtual presence. But this particular event has been very well organized, and I have truly very high hopes of future, particularly in India. I think there is a need for students' participation, and I hope by the time this year and next year rolls out, we will have some significant outcomes. Thank you.
Yeah. Thank you very much, sir, Professor Gupta. We see Professor Paul back.
I'm back after my shirt.
Right.
I got motivated by Nuno because he used a T-shirt, so I also used a T-shirt. So it was a very interesting and nice talk. Thanks, Nuno. It was very motivating. And Ramesh mentioned, I think we are moving ahead with now IMARC 2021. Hopefully, we'll have a great event. For your information, 2022 is going to be held in Delhi, and this will be 10th year of IMARC. So at that time, we'll invite everybody from abroad and also the chapter chairs to have this as one of the key conferences in 2022. So we still have time, but I think we can plan now to do some new events. I'm an old man now, I can't think of new events. So you guys are young. So you can think of something new at these conferences based on what we do at IMS. Thank you.
Thank you very much, sir. Now, just before we conclude, I have one more technical query to Professor Nuno. So some of the people here are trying to do some kind of work for some mid-range wireless power transfer. For example, some powering some UAVs or drone or etc. in general. So, where do you see these practical applications in near future in general?
Well, as I said, so we have two approaches for wireless power transmission. One is the near field, and most of the time is inductive coupling or resonant inductive coupling. And on that direction, the efficiencies are quite high, and there are already commercial products. So for drones, I've seen a lot of activities where the drone actually stops in a base that powers up, charges, goes, fly, and then comes and powers. And this is very efficient and is working very well. There are a lot of companies already selling solutions to this. So from that point of view, I think we are very well developed, let me put that way. For far field, or let me put this way, long range wireless power transmission, higher than 10 or 20 meters, the technology is not there yet. There are a lot of research to do. So there are a lot of groups going in different directions. And that's why the WPT community in IEEE is being brought together. So all of you if you want to join us, as I said, at the end of the month, we are going to launch a new website on the wpt.ieee.org, so that you can collaborate with us. If you want to become a volunteer in that community, send me an email. I'm also the chair of that community, so I can try to promote your volunteer activities there, because I think it's an amazing research area at this point, because we are far away to have high efficiency, long range wireless power transmission. And this is, I think it's a very, for me, it's a very high motivated area to work. Yeah. And before we stop, thank you very much for the invitation. I think the meeting today was very well organized, very well prepared. You have a significant number of attendees. At a certain point, I saw 130 participants, which is very, very good. And I would like to thank also Professor Shiban Cole, because actually is doing a very good work in India, and Professor Pollard, because the Indian teams are very active, and your team especially is very, very good in terms of webinar production and these type of activities. So from MTT side, I would like to thank you all for this amazing structure that you are building in India.
Thank you, Professor Nuno. As you said, we want our volunteers to be technically active as well. So definitely, I am sure that given a lot of impetus. So some of the research scholars whom I know personally, so masters also, I am pretty sure they have already been inspired to take up some work, and will be really happy to get involved in the IEEE that WPT initiative to talk about. So before we conclude, I have just a request to Professor Birenjit, who is the branch counselor for this GEC student branch, whom we missed during the inauguration, to just say a concluding remark, and probably they're displaying the congratulatory note. Dr. Birenjit. So this is a congratulatory note from the college principal. Yes.
You are muted, sir.
Yeah. Hello. Thanks, Chinmoy. I'm glad that I could attend this event, though I missed to attend the inaugural function because I got stuck up in something else. Anyway, it's more heartening that I could join when some technical interactions was happening. It's very to see such activities here. So I am the branch counselor of GEC Barton Hill, and as all of you here know, that the students of GEC Barton Hill and Professor Anu Mohammed has been very active in the MTTS activities. So I'll just read out the congratulatory note sent out by principal of our college and conclude. So he just passed a letter. It's a proud moment for all of us when IEEE student branch in GEC Barton Hill commence IEEE Society on Microwave Theory and Techniques with a virtual gathering of renowned speakers. I'm sure the society will initiate and realize many fruitful activities in future. I wish all success. So I also wish every success to GEC Barton Hill MTTS chapter, and in general the Kerala chapter of MTTS. Thank you all. Chinmo, you can take it.
Yeah. Thank you, Birenjit. We really missed you during the inauguration. Anyway, we are really pleased to see the congratulatory message from your principal. So on behalf of the MTTS Kerala chapter, and also on behalf of all my student volunteers and all the organizers, fellow office bearers, I once again extend my most sincere thanks to all the dignitaries, to the highest leadership, and of course Professor Paul, Professor Gupta, Dr. Poddar, Professor Nuno. Like he was, he logged in around 6:30 IST and he's still there, so it is almost 3 hours. So thank you very much. You have been always very generous, and as you have been the probably the most suitable speaker to start this technical session, and started with Professor Call also. So we'll, as we mentioned that this is a series, so it will comprise of the technical sessions, panel discussions, focused colloquium and all. So stay tuned with MTTS Kerala chapter for future activities, future happenings. So with this, we may conclude, and maybe the student volunteer Gopika will offer a formal vote of thanks. And this is an event which is tomorrow. The President Antenna Propagation Society will be coming to inaugurate the All Kerala APS Student Conclave, with the presence of Dr. Siddiqui and the other speakers, Dr. Sarkar, Dr. Ghosh, myself, for a panel discussion and other things. So Gopika, you may formally offer the formal vote of thanks. Okay, I think there is some activity. So Shivada Rakshat, you can close with a very short message.
Thank you, Sahasar. Thank you, Shiban Kaul sir, and a lot of dignitaries, Ajay Podar sir. I'm the chapter chair of this society, and it's been a really tough journey, but because of the support that I get from everyone, I mean, the overwhelming support that I got from all over the world, it's in the literal meaning, all over the world. This chapter's inauguration has been a success, and it's only because of your support that this chapter is going to flourish. So this thank you is from the bottom of my heart. Thank you so much, and we are looking forward to having even more associations with you in the future. So thank you, sir. That's all that I have to say.
Yes, Akshat. Thank you very much. So once again, thank you. Good evening, good night. Have a good day to all of you. Maybe I request Professor Call to say the concluding remarks.
I think it was a very nice event, and keep it up. I'm very happy that after so many years now we have so many young volunteers, and I think the future of MTTS and AP will be very good as far as India is concerned. As I mentioned in the beginning, that we want to be the best in terms of educating engineers who will find placements globally. That's the ultimate aim. Thank you.
Thank you very much, everybody.
Yeah.
Thank you, sir.
Yeah. Thank you very much. Thank you. Thank you, everyone. Professor Siddiqui, Professor Poddar, and everyone. So, good evening, good night, good day. Stay safe, and see you again. Thank you, Professor Nuno, for the wonderful talk. I am getting a lot of applause through my WhatsApp chat box regarding your talk.